Mr. Tarrou, in this algebra lesson, we're going to be talking about arithmetic combination of functions, or in other words, we're going to be adding, subtracting, multiplying, and dividing functions, talking about function notation along the way, how to interpret or read this, domain and range of some functions, and I chose some particular equations that students make common mistakes on, either trying to simplify or in finding their domain. We're going to be looking at a sort of segmented diagram to help us understand if we have a couple of functions on a graph, how to graph the sum of those two functions. And then finally, our third example is going to be referring to this graph yet again, but working with that function notation, but evaluating function values, in this case just division, at a particular value. Though the same could hold with our examples, could be doing addition, subtraction, or multiplication as well. I just want to point out some interesting characteristics of these division problems. So, we're going to be looking at f of x is equal to the square root of 9 minus x squared. Now, I've had a lot of students that will see something like an expression of the square root of 9 minus x squared and say that is equivalent to 3 minus x. They see the fact that we have two perfect squares underneath the square root, and they'll take the square root of each of those individual terms and write that it's 3 minus x and feel like it's okay. If you ever do anything in algebra that you're unsure of, maybe writing something like this that you think it's correct, you can check with arithmetic. Is the square root of 9 minus x squared the same as 3 minus x? Well, could you say, calculate the square root of 9 minus 4? If you see the square root of 9 minus 4 and you follow those order of operations, please excuse my dear Aunt Sally, you would work inside the grouping symbol, in this case the square root, and you would say that this is equal to the square root of 5. Well, if you take the square root of each individual term, see the problem is these are two different terms separated by subtraction. They're not two factors. If you take the square root of 9 and you get 3, and the square root of 4 and you get 2, well, 3 minus 2 is equal to 1, which is certainly not equal to the square root of 5 that we would get if we properly followed those order of operations. Students are always, I've never had a student in my math classes say that the square root of 9 minus 4 is equivalent to 3 minus 2, where they take the square root of each individual term. But when you have an algebraic expression and that variable representing an unknown quantity or expression, those sort of basics sometimes get a little confused and fall away, and they write this common error. So the square root of 9 minus x squared will not simplify. We're going to deal with that function just as it is. Same thing here with g of x. Not only did I pick a couple of functions that we can have a conversation on, a good conversation about finding domain of functions, but we also have something here where students, let me grab the red chalk again, will see that they've got a fraction where you have the same, not factor, but the same term in both the numerator and denominator, and they'll think that it's safe to go ahead and cancel out those common terms. Terms are separated by addition and subtraction. Factors, now maybe having a factor of 1 doesn't show too well here, but if it was, say, let me write this as a 4. You know, if it was 4x squared in the denominator and it was x squared over 4x squared, well then those common factors of x squares could cancel. But that was x squared plus something else. That is a term. It is not a factor, and thus that does not cancel. You could do the same thing, maybe say something like 2 over 2 plus 4, and check to make sure it's, can you cancel out those common terms? Now, sometimes when students cancel common terms, they just let things disappear, like maybe they would write this as 1 over 4. Maybe they'll show that 2 divided by 2 is 1, and they'll even put the 1 there. But if you check that with arithmetic, if you let the common terms cancel, you would have something to the effect of either 1 over 4 or 1 over 5. And I'm saying or because this is an error. You cannot do that. If you look at 2 over 2 plus 4, that's 2 over 6, which reduces to, after you divide the numerator and denominator by 2, would reduce to 1/3. And that's not going to, 1/3 is the correct answer. That would not be what you would get if you cancel out a term. So you cannot, let something divide by itself to equal 1. You cannot cancel out like terms, can't find my eraser cloth, but you can only cancel like factors, something that is multiplied to something else, not added. Okay, so with those basic foundations out of the way in terms of common errors of students, we have f of x. What is the domain of this function? We have to be aware of the domain of f of x, and g of x for that matter, as we go to write up the addition, subtraction, multiplication, and division, combining these two functions and determining the domain of the sum, product, or quotient of those two functions. So you need to be aware that most functions have a domain of all real numbers. Now, as you get into, say, natural logs or trig functions, being a little bit more cautious about what the domain would be is going to be a little bit trickier, but when you're just dealing with algebraic expressions, pretty much you're looking for an even root or a division. You cannot take an even root of negative numbers unless you're working with and considering imaginary solutions, and you cannot divide by 0. So for f of x, we have the square root of 9 minus x squared. We're only going to be considering real solutions. So in terms of the domain, 9 minus x squared has to remain greater than or equal to 0. The square root of 0 is 0, and the square root of a positive number is going to yield a positive answer, as long as you're working with that principal square root. It's just that you cannot take the square root of a negative number, like the square root of negative 4. Yes, it's 2i, but 2i, let's say in the letter I, implies and gives, allows us to see that I'm considering imaginary solutions. So for only real solutions, we have that negative x squared then has to be greater than or equal to negative 9. Dividing both sides by negative 1, we have x squared is less than or equal to 9. And then as we take the square root of both sides of this inequality, and because we're bringing in the square root, we have to account for both the positive and the negative answer, because the square root of x squared really acts as an absolute value function. So when we introduce our own even root, we have to consider both the positive and negative answers. So we're going to keep that inequality in the same direction for the positive square root of 9, but we have to consider the changing of that inequality. So instead of x is less than, x is going to be greater than the negative solution. So the domain of f of x is equal to 9 minus x squared. That domain is going to be, in interval notation, x has to be greater than or equal to negative 3 and less than or equal to positive 3. If you're using, hopefully, interval notation in your book, we have square brackets to indicate the equal sign. If the equal signs were not included, these would be parentheses. This is equivalent to x is greater than or equal to negative 3 and less than or equal to 3, but that's in interval notation. With our second function, g of x, we've got x squared over x squared plus 1. Now, there's a math function in our second equation here that I just mentioned that we should be cautious of in terms of determining domain. You cannot divide by 0. So if there's any numerical value that can make that entire denominator equal to 0, it's going to need to be removed from the domain of g of x. So is it possible, working at the domain of our second function, for x squared plus 1 to be equal to 0, because that denominator cannot equal 0. So then x squared cannot equal, as we subtract both sides by negative 1, x squared cannot equal negative 1. To get rid of the power of 2 on our x, we're going to square root both sides. And again, we are looking for real, the limitations to the real domain. Yes, the square root of negative 1 is equal to I, but that is an imaginary number. So in terms of real numbers, this denominator, no real value of x is going to make this denominator equal to 0. So the domain of g of x is all real numbers. So even though we have a division in our function and there's a variable in that denominator, we need to be careful and check for the domain of g of x. But as it turns out, our domain is all real numbers. So negative infinity to positive infinity and beyond. Or you could write double R, or you could just write all real numbers. But g of x does not have a restriction on the domain. So what is f plus g of x. How do you what is this notation telling us to do with the function of f and g? Well, when you see this f plus g in parentheses and another parentheses of x, that's equivalent to f of x plus g of x. Or in other words, just take these two, we're just going to write these two functions side by side and say, well, f is the square root of 9 minus x squared, and plus g of x is x squared over x squared plus 1. Now, I chose these two functions to have a conversation about an interesting conversation about domain, and to point out some of those common errors that my students do trying to simplify these functions when they see them. But at this point, it's not very interesting because there's really no need to attempt to put these two terms together. We're not going to clean anything up and end up with a nice simple simplified function. So I'm just going to leave that as the square root of 9 minus x squared plus x squared over x squared plus 1. And for these two functions to be subtracted, again, that's just going to be f of x minus g of x, which is going to be the square root of 9 minus x squared plus x squared over x squared plus 1. And for our third example here, how do we read this parentheses with f and g touching inside parentheses in our x? I'm breaking out a little lesson here for YouTube out of this section of the pre-calculus book I'm teaching from. And in this section of pre-calculus, we have combinations of functions, or excuse me, composition of functions and combinations at the same time. Maybe in an Algebra 1 or Algebra 2 book, those would not be combined in the same section. But my students are seeing two function names touching, and then they're also seeing, and it's not going to be covered in the scope of this video, but they're going to see two function names in a set of parentheses, but with an open dot in between them, and that's notation for composition. If there's no open dot between your two function names and they're effectively just touching, that is an indication of multiplication. So part C here is f times g of x, or in other words, f of x times g of x, which is going to be, well, f of x is the square root, again, of 9 minus x squared, times our function g of x, which is a fraction, x squared over x squared plus 1. So now I'm actually going to put these two factors together. And if I intended to add these two parts here up in the addition and subtraction portion, I would have done this as well. But once you start doing some work with fractions, if you're not already doing this, you should make basically everything look like a fraction to make sure you keep those numerators and denominators lined up correctly. So we have here for a third example, x squared times the square root of 9 minus x squared over x squared plus 1. And you can make it happen, but there's no real easy way to make this x squared distribute into the square root. This 9 minus x squared is in a math function of their own, separate from the multiplication of x squared outside. So that's just going to sit there, and we're done. Now the domain the domain of part A, B, and C is going to be that original domain where f of x has a domain of -3 to 3, and g of x has a domain which is all real numbers. Well, part A, B, and C, all of these combination of functions, when you talk about the domain of a function, you have to have a domain restriction that satisfies a restriction of any one of the individual parts. So even though A, B, and C all include an x squared over x squared plus 1, the domain of part A, B, and C is going to be, and I'll do this in yellow just to make sure it's nice and easy to see, or maybe I should do orange. The domain of each of these functions is going to be -3 to 3. Because all three of these parts have as either a term or a factor that function of f of x, or that expression of the square root of 9 minus x squared, and that is only going to yield real solutions between the x values of -3 and 3 including. Now, to get into the more interesting or most interesting part of this first example is the division of these two functions, and also that would give me an opportunity to review with you all out on YouTube how to divide or work with a complex fraction where you have a fraction within a fraction. So I didn't pick the world's easiest problem to do on video, which is perfect because that's an opportunity to learn the most possible, or at least you don't really learn anything by watching me or your teacher present material. It's just an opportunity to absorb that information, and then it's the practice, the homework, the repetitiveness that you will do as you do your homework and check your solutions along the way. That thinking, physical process of writing down and solving problems is really where the learning occurs. I'm just presenting information to you. So in part D, where we go to multiply these functions together, or excuse me, not multiply but divide, we have part D is, well, f over g in parentheses x is equivalent to f of x divided by g of x, which means we have f of x, which is going to be the square root of 9 minus x squared over g of x, which now we're bringing in a fraction into the denominator of the fraction of our new combination function here, and we have x squared over x squared plus 1. Now, when you go to find a domain of ultimately, in our next video, which is going to be compositions, or when you're doing combinations, you should always determine the domain of your new combination or composition function before you do any kind of simplification. Within our denominator here, we now have a division of x squared over x squared plus 1. G of x is defined everywhere along the real number, including all the real values, everywhere along the x-axis, the real x-axis, the horizontal axis. But now, if you take that entire fraction and you stick it into the denominator, hey, now this entire fraction is in the denominator. This entire function, g of x in the denominator, cannot equal 0. So we have a new restriction. If the numerator of a fraction equals 0, then the entire fraction is equal to 0. So for this combination of f over g of x, we have that restriction for the square root of 9 minus x squared, our given domain that we've already discussed. G of x has a domain of all real numbers, but as this combination, x squared, if that numerator is equal to 0, then you're going to be dividing by 0, and that again sets up a situation of a function being undefined. So x squared, we're not going to figure out where it's equal to 0. We are sort of, but it's with that idea that x squared cannot be equal to 0, so x cannot be 0 itself. So I'm about to simplify this, but the restricted domain for part D is, well, the whole real axis, from negative infinity to positive infinity is going to be thrown out, because within this function, again, we have that square root of 9 minus x squared, and this is a much more restricted, or a subset, the x values between -3 and 3 inclusive from this all real number domain from g of x. But included in this tighter domain, we also have to include the fact that x cannot be 0. So D will have a domain of, I'm going to write this in interval notation, where we go from -3 to 0, but, -3. -3 to 0, and I'm going to use a round parentheses here because we can't include 0. We just said that x could not be 0. And then or, that's read as or, from 0 to 3 inclusive. Or in other words, we can write that as x is greater than or equal to -3 and less than 0, or x is greater than 0 and less than or equal to 3. Now I kind of want to say and, like this interval and this interval is part of the domain. But when you talk about set notation, if I write the and symbol, then it would be the idea that you know, the domain has to be a number that satisfies this interval and this interval. Well, there's no overlap, if you were to put that on a number line, between the shading of -3 to 0 and from 0 to 3. So that, you know, say an and or write in an and symbol might make sense in sort of like plain language, but it doesn't work for math because the solution to that is nothing. Empty set, no solution. Okay, and that is with algebra. Almost I would call it analytical combination of functions as opposed to arithmetic, but that is the addition, subtraction, multiplication, and division of those two functions. Yeah, so through editing I see that I did not reduce that fraction. Let's of course not forget that fraction bars represent division. Highlighting that main division bar in orange and writing the numerator as a fraction. So we have those numerators and denominators lining up. We have the square root of 9 minus x squared over 1 divided by x squared over x squared plus 1. And while we write, you know, a division of fractions, we actually multiply by the reciprocal. So we change that division to multiplication and flip the second fraction and write that as the square root of 9 minus x squared over 1 times x squared plus 1 over x squared, giving us a final answer of f over g of x is equal to x squared plus 1 times the square root of 9 minus x squared over x squared. And as we can see here, there's really no simplification to occur, so we still had that denominator of x squared, which would have allowed us to find the additional restriction of the domain where x cannot equal 0. But sometimes that maybe that factor, in this case the x or the x squared creating that division of 0, creating that additional restriction on the domain, does cancel out. And if you were to try and find the domain of a quotient after simplifying, you may not find all those restrictions on the domain. So you always want to find a domain before simplifying when dealing with fractions. On to our regular scheduled program. How would we graph? If we have a graph of f and g, now we don't have like actual sort of like function graphs. This isn't like f of x is equal to sine and g of x is equal to x squared plus 2x. We have a segmented graph given here so that we can more easily graph a sum. We want to graph h of x, which is represented by f plus g of x. And again, that is equivalent to f of x plus g of x. I want to make a graph of h, and I'm going to just simply use the values. Oh, I didn't label my x and y axis. Okay. So I'm going to just go to the x values of -4, -1, 1, 3, and 5, and make a plot, a sketch of h of x, which is f plus g of x. So at x equals -4, which I think I'm going to write it a couple of times just to make sure you totally follow what's going on. So where am I going to plot h of -4? It's going to be coming from looking at what f is giving us at -4 and what g is giving us at -4. And f of -4, which is the orange graph, is giving us an answer of -3. And g of -4 is giving us an answer of 1. And so -3 plus 1 is going to give us, for h of -4, an answer of -2. So 1 minus -3 is -2. Now I'm not going to write this out every time just to speed up the video, but this is what I'm doing as I look at every one of those points in the graph where I put a nice big round dot for us. Now moving on to our next identified point here at -1, h of -1 is f of -1 plus g of -1. Well, f of -1 is 0, and g of -1 is 2, and 0 plus 2 is equal to 2. Okay, we have a couple of nice bold points here at x equals 1. H of 1 is going to be f of 1 plus g of 1, and f of 1 is giving us 1, g of 1 is giving us -1, and 1 plus -1 is going to give us 0. Coming over here to x equals 3, h of 3 is going to be f of 3 plus g of 3, and that's 1 plus 2 is equal to 3. And then finally at x equals 5, h of 5 is f of 5 plus g of 5, and that's going to be f of 5 is negative 1, g of 5 is negative 3, and negative 1 plus negative 3 is 2 movements to the left. Well, it's more than 2 movements, it's arguably 4 movements, but negative 1 plus negative 3 is going to be equal to negative 4. And this is our segmented sketch of h of x, which is equal to f of x plus g of x. And I missed a little bit there, but you know, it is just, I'm trying to do these lines straight, but I'm not really using a straight edge. Now down here for our last example, we have f over g, f divided by g of negative 1. Well, f over g of negative 1 is going to be equivalent to f of negative 1 over g of negative 1. We really need to understand that notation because I don't have a function f and a function g. I don't actually have functions that I can divide or add or subtract, and then once I do that, say, division and simplify, then plug in negative 1, I have to understand that looking at the graph, I need to go find function f and find its y value at negative 1, go to function g, find its y value at negative 1, and do the division. Now, this may come out to be a boring solution, but I do want to look at negative 1 specifically because of the different kind of answers we get for our two expressions. F of negative 1, that's the orange one, is giving us an y value of 0, and g of negative 1, well, that's, you know, g function notation gives obviously y answers as an answer, is equal to 2. And let's not remember, or excuse me, let's remember that you can have a numerator in a fraction. You can divide 0 by anything, and the answer is, you know, what do you multiply 2 by to get an answer of 0? In terms of that multiplication be the inverse of division. Well, 0 divided by 2 is equal to 0. 0 divided by anything is equal to 0. So while this f divided by g of negative 1 came out to be 0, what happens if the g function is in the numerator? Well, that's going to be g of negative 1 over, or divided by f of negative 1. And g at negative 1 gave us that answer of 2. F of negative 1 was giving us that y value of 0. And you cannot divide by 0, right? 2 divided by 0 is a form of undefined. You cannot divide by 0. Even if it's 0 over 0, that's an indeterminate form of undefined. There's some special properties with that, but you still arguably cannot divide by 0. So 0 divided by 2 is 0, but 2 divided by 0, that just simply does not exist. And so I hope that helps you understand the combination of functions dealing with addition, subtraction, multiplication, and division. I'm Mr. True. Bam! Go to your homework.